Problems with replication lag. Being able to tolerate node failures is just one reason for wanting replication. As mentioned in the introduction to part 2, other reasons are scalability. Processing more requests than a single machine can handle and latency. Placing replicas geographically closer to users. Leader-based replication requires or writes to go through a single node, but read-only queries can go to any replica. For workloads that consist of mostly reads and only a small percentage of writes, a common pattern on the web, there is an abstractive option. Create many followers and distribute the read requests across those followers. This removes load from the leaders and allows read requests to be served by nearby replicas. In this read scaling architecture, you can increase the capacity for serving read-only requests simply by adding more followers. However, this approach only realistically works with asynchronous replication. If you try to synchronously replicate to all followers, a single node failure or network outage will make the entire system unavailable for writing. And the more nodes you have, the likelier it is that one will be down. So a fully synchronous configuration will be unreliable. Unfortunately, if an application reads from an asynchronous follower, it might see outdated information the follower has fallen behind. This leads to apparent inconsistency in the database. If you run the same query of the leaders and the follower at the same time, you may get different results. Because no all writes have been reflected in the follower, this inconsistency is just a temporary state. If you stop writing to the database and wait a while, the follower will eventually catch up and become consistent with the leader. For that reason, this effect is known as eventual consistency. The term eventually is deliberately vague. In general, there is no limit to how far a replica can fall behind. In normal operations, the delay between a write happened on the leader and being reflected on the follower, the replication lag, may be only a fraction of the second and not noticeable in practice. However, if the system is operating near capacity, or if there is a problem in the network, the lag can easily increase to several seconds or even minutes. When the lag is so large, the inconsistencies is introduced are not just a theoretical issue but a real problem for replications. In this section, we will highlight three examples of problems that are likely to occur when there is a replication lag and outline some approaches to solving them. Reading your own writes. Many applications let the user submit some data and then view what they have submitted. This might be a record in a custom database or a comment on a discussion thread or something else of that sort. When new data is submitted, it must be sent to the leader, but when the user views the data, it can be read from a follower. This is especially appropriate if data is frequently viewed but only occasionally read. With asynchronous replication, there is a problem, illustrated in figure 5.3. If the user views the data shortly after making a write, the new data may not yet have reached the replica. So the user is look at through the data they submit was lost. So they will be understandably unhappy. In this situation, we need read after write consistency, also known as read you write consistency. This is a guarantee that if the user reload the page, they will always see any updates they submit themselves. It makes no promises about the users. Other users they may not be visible until some later time. However, it reassures the user that their own input has been saved correctly. How can we implement read after write consistency in a system with leader-based replications? There are various problem techniques to mention a few. When reading something that the user may have modified, read it from the leader, otherwise read it from the follower. This requires that you have some way of knowing whether something might have been modified without actually querying it. For example, user profile information on a social network is normally only editable by the owner of the profile, not by anybody else. Thus, a simpler rule is always read the user own profile from the leader and any other user profile from the follower. Is if most things in the application are potentially editable by the user, that approach won't be effective, as much things will have to read from the leaders, negating the benefit of read scaling. In that case, other criteria may be used to decide whether to read from the leader. For example, you could track the time of the last update and for 1 minute after the last update, make all reads from the leaders. You could also monitor the replication lag on followers and prevent query on any follower that is more than 1 minute behind the leader. The client can remember the timestamp of its most recent write. Then the systems can ensure that the replica serving any reads for that user reflects to date at least until the timestamp. If a replica is not sufficient up to date, either the read can be handled by another replica or the query can wait until the replica has caught up. The timestamp could be a logical timestamp. Sometimes that indicates ordering of writes, such as the log sequence number or the actual system clock, in which case clock synchronization becomes critical. If your replicas are distributed across multiple data centers or geographical proximity to user or for availability, there is additional complexity. Any request that needs to be served by the leader must be routed to the data center that contains the leader. Another complication arises when the same user is accessing your services from multiple devices, for example, a desktop web browser and a mobile app. In this case, you may want to provide cross-device read after write consistency. If the user enters some information on one device and they view it in another device, they should see the information they just entered. In this case, there are some additional issues to consider. Approaches that require remembering the timestamp of the user last update become more difficult because the code running on one device doesn't know what updates have happened on the other device. This means the data will need to be centralized. If your replicas are distributed across different data centers, there is no guarantee that connection from different devices will be routed to the same data centers. For example, if the user desktop computer uses the home broadband connection and their mobile devices use the cellular data network, the device network route may be completely different. If your approach requires reading from the leader, you may first need to route requests from all user devices to the same data centers. Monotic reads. Our second example of anomaly that can occur when reading from an asynchronous follower is that it's possible for a user to see things moving backward in time. This can happen if a user makes several reads from different replicas. For example, figure 4.5. 5.4. Figure 5.4 shows user 2345 making the same query twice. First, to a follower with little lag, then to a follower with greater lag. This scenario is quite likely if the user refreshes a web page and each request is routed to a random server. The first query returns on a comment that was recently added by user 1234, but the second query doesn't return anything because the lagging follower has not yet picked up that write. In effect, the second query is observing the system as an earlier point in time at the first query. This wouldn't be so bad if the first query hasn't returned anything because user 2354 2345 probably wouldn't know that user 1234 had recently added comments. However, it's very confusing for using 2345 if the first you see users 1234 comments appear and then see disappearing again. Monotic risk is a guarantee that this kind of anomaly does not happen. It leaves a guarantee that strong consistency, but a strong guarantee that eventually consistency. When you read data, you may see an old value. Monotic risk only means that if one user makes several reads in sequence, they will not see time go backward. They will not read older data after having previously read newer data. One way of achieving monotic reads is to make sure that each user always makes the read from the same replica. Different users can read from different replica. For example, the replica can be chosen based on a hash of the user ID rather than randomly. However, if that replica fails, the user query will need to be routed to another replica. Consistent prefix read. Our third example of replication log anomalies concern violation of causality. Imagine the following short dialogue between Mr. Poon and Mr. K. Mr. Poon, how far in the future you can see Mr. K? Mr. K, about 10 seconds usually, Mr. Poon. There is usually there is a causal dependency between these two sentences. Mr. K heard Mr. Poon's question and answered it. Now, imagine a third question is listened to this conversation through followers. The things said by Mr. K go through a follower with little lag, but the things said by Mr. Poon have a longer replication lag. This observed will hear the following. Mr. K, about 10 seconds usually. Mr. Poon. Mr. Poon, how far in the future can you see Mr. K? To the observer, it looked as though Mr. K is answering the question before Mr. Punz has even asked it. Such secret power are impressive but every confused. Preventing this kind of anomaly requires another type of guarantee, consistent prefix reads. These guarantees say that if a sequence of writes happen in a certain order, then anyone reading those writes will see them appearing in the same order. This is a particular problem in partitioned charted databases, which we will discuss in chapter 6. If the database always applies write in the same order, reads always see a consistent prefix. So this anomaly cannot happen. However, in many distributed databases, different partitions operate independently, so there is no global ordering of writes. When a user reads from a database, they may see some part of the database in an older state and some in a newer state. One solution is to make sure that any writes that are casually related to each other are reading the same partition, but in some applications that cannot be done efficiently, there are also algorithms that explicitly keep track of causal dependencies, a topic that we will return to that happened before relationship and concurrency on page 186. Solution for replication lag. When working with an eventual consistent system, it is worth thinking about how the application behaves if the replication lag increases to several minutes or even hours. If the answer is no problem, that's great. However, if the result is a bad experience for users, it's important to design the system to provide a stronger guarantee, such as read after write. Pretending that replication is synchronous when in fact it is asynchronous is a recipe for problem down the line. As discussed earlier, there are ways in which an application can provide a strong guarantee than the underlying databases. For example, by performing certain kinds of reads on the leader. However, dealing with this issue in application code is complex and easy to get wrong. It would be better if application developers didn't have to worry about subtle replication issues and could just trust their databases to do the right thing. This is why transactions exist. They are a way for databases to provide stronger guarantees so that the replication can be simple. Single node transactions have existed for a long time. However, in the move to the distributed replica and partitioned databases, many systems have abandoned them, claiming that the transactions are too expensive in terms of performance and availability, and asserting that eventually consistency is inevitable and a scalable system. There is some truth in that statement, but it is overly simplistic, and we will develop a more nuanced view over the course of the rest of this book. We will return to the topic of transaction in chapter 7 and chapter 9, and we will discuss some alternative mechanisms in part 3.